So let's welcome our first keynote speaker, Steve Macenski. Steve is the engineering lead at Samsung Research America Open Source Robotics, and he also is the leader of the Navigation 2 project.
Yeah, the Navigation 2 project is one of the most important projects in ROS2. Basically, navigation means allowing a robot to move from point A to point B while avoiding obstacles. So we have this in ROS1, it's called the ROS navigation stack, and then the Navigation 2 project is the translation, let's say, an improvement of this stack into ROS2. Then Steve is going to talk us about some feature requested by the users on the Navigation 2 package. Hello, Steve. How are you doing? Are you ready?
Hi, yeah. Can you hear me?
Yes, we can hear you.
Awesome.
Great. Then the audience is all yours. Go for it.
Awesome. Yeah, I really love this Mars theme. This is really fun. But hi, everybody. So happy to be the first keynote speaker here of the day. It's 10 p.m. here in San Francisco, California. So forgive me if I'm a little tired. I'll just have to hold you to ask you some good questions and drinking some coffee.
Yes, of course. We'll have some questions at the end of your speech.
Sure. All right, so let's get started. So I'm here to talk to you about some of the new features and some of the basic features in Navigation 2, which is the ROS2 navigation stack, also known as Nav2. And I'm here to give you some practical demonstrations of some of the new user requested features that we've added. Just to start off here quickly, my name is Steve Macenski. I do a great deal of different robotics stuff at Samsung Research America. I'm the open source robotics engineering lead. That means I consult with internal Samsung teams on technology and business impact, as well as working on different mobile robotics and perception research, as well as working in the ROS2 TSC and the Navigation 2 working group lead. Before this role, I was the lead robotics engineer at Symbi Robotics and worked on the NASA Asteroid Redirect mission and Restore-L missions, which were both autonomous servicing missions in space. To give you some overview of what we'll be working on today, so we'll be working with Nav2, which is obviously the second generation of the ROS nav stack. This has a lot of different capabilities and algorithms and features that are brand new to ROS2 and exclusively available in ROS2. And we're really looking to have Nav2 focused on building both production resources as well as research applications. So that means that we're really focused on having these things be high quality, documented, tested for production users, but still be very easy to use for the researchers in the room. You can find more information about this on navigation.ros.org, where we have a bunch of different tutorials and migration guides, integration guides. I've spent quite a bit of time documenting things about Nav2, so check it out. It's a great first stop, as well as a place to be checking out regularly if you're a Nav2 user. So in this talk, we're going to be talking about some of the more basic features of Nav2, but some of these basic features are brand new to Nav2, so unless you've been using it a lot, these things might be new to you, actually. So we'll be discussing the navigate to pose action, and we'll be interacting with it through RViz2. And then we have some autonomy scripts that I've set up in Python 3 in order to have you demonstrate demos with navigate through poses, as well as the follow actions, or follow waypoints actions, both of which we'll discuss in more detail at the end. And if there's time at the end, which I think there will be, we're going to be discussing some keep out zones and speed restricted zones as well. And I'll have some demo videos available for that as well. So what we'll be working with today is this simulated Gazebo environment. So this was provided by the AWS RoboMaker Small Warehouse World. This was one of many different really awesome Gazebo worlds that AWS RoboMaker has open sourced to the community. It's this little small warehouse world that you'll see, and it's really nice for doing some demonstrations in some sort of like industrial type environment. And we're also going to be working with the Neobotics MP400 mobile robot, which uses Nav2. And so they've ported all their stuff over to ROS2, obviously, in order to do so. So we've worked with their team in order to set that up with the simulation. So there's links here to this MP400 robot as well if you're interested. But it's a reasonably sized, I think it's about 0.8 meter radius industrial differential drive robot that really fits well in this space, I think. So all the code that we're using here is also going to be available on my GitHub page that's linked to here. You can have different instructions for setting this up locally after the presentation if you want to use it on your local machine, if you're a Linux developer. If not, then through this platform is definitely the best way to access this work. So just to start off here, let's talk a bit about Navigation 2 as a project. So Nav2 was built to be the successor of the ROS1 navigation stack, which had a variety of really high impact in the robotics industry, from startups to big companies built over at Willow Garage. But over time, people want to have more flexibility or build new applications that move base as one giant application just really couldn't handle. So in the design of Nav2, we took into account a bunch of this different feedback from users that was led by Matt Hansen over at Intel at the time, and he did a really great job sifting through all that feedback and coming up with a really nice design to help mitigate many of those problems. So rather than having one giant server containing all the cost maps, all the plugins, and the autonomy logic, we now have these independent modular servers instead. So we have this BT Navigator server whose primary task is to host this behavior tree, which is this configurable base of logic for the navigation task, as well as then having these independent servers for doing things like path planning and control and recovery. And each of these servers then hold their appropriate cost maps they're utilizing. What's really nice about this design is that if instead you want to use a controller written in Python because you're working in some machine learning application, you can easily just not bring up the Nav2 controller server and bring up your own controller server written in Python, but then still use all the other infrastructure that Nav2 provides, including the BT Navigator, the planner servers, and whatnot. So it's really easy to be able to replace just individual modules and still use the very large architecture of Nav2. It also allows you to then run this on different CPU architectures as well. So you might want to have your controller server running on a low-level ARM CPU that's in your robot because you want to have that really close to the hardware. But maybe your path planner, you don't care about that being super high frequency and low latency. So maybe you have some sort of machine learning path planner that's running in the cloud. So you can actually have all of these things running on different CPUs on different machines and still interact with one coherent navigation system. We also have a number of growing runtime reconfigurable algorithms and plugins available. This includes all the things that you expect from ROS1, like TEB, DWB, and NavFN Planner. But then we also have some brand new algorithms, including the Regulated Peer Pursuit Controller, the Hybrid A-Star SMAC Planner, as well as many others that are in the works, as well as I think over 30 behavior tree nodes you can use to build your autonomy tasks in the behavior tree application. Like I said, we're very focused on being production focused. So we have this software quality perspective that we're really looking through. That includes linting and testing. So all pull requests have to meet our strict style guides, as well as improve the test coverage of the actual repository. So right now we're at 86% line coverage, which is some of the best in the ROS ecosystem. And if you're interested in joining us, we have a Slack as well as a working group. If you can sign up for the working group there, and when you join the working group meetings, I can share with you a link to our Slack. We can ask questions or get involved or contribute or whatever you're interested in doing with the community. We also have that rich documentation, navigation.ros.org, you can utilize as well. So with that, we should get started here with our demonstration. So the first thing we're going to do here is we're going to go into our ROS2 workspace. So we're going to CD into that ROS2 workspace, and we're going to see that I actually already built this kind of stuff. So you can actually just go ahead and source your opt-ROS Galactic in order to make sure you have all the good stuff from Galactic installed in your source path, and then we're going to build that. And you're seeing it's going to go pretty fast because we already have it built for you, but it's always good just to make sure that we're building that again. So while we're doing that, we should take a look at some of the code we'll be working with today. So we're going to go to source, and you'll see that there's this Nav2 ROSDevDay 2021 directory, and we're going to go into that second level nested directory this as well. And this is where we're going to see our main package. So you're going to see here, the first kind of thing we have here is this maps directory. In this thing, you'll see we have our keep out maps as well as our lanes maps we're going to be using in later demonstrations of the keep out zones. Then you're also going to see that we have this launch directory. And this contains just one major launch file, this system launch.py. And what this is going to do is launch Gazebo and RViz and the navigation stack so that we can test some of our autonomy scripts with some sort of baseline setup. And the next one here, let's get our parameters. So we just have a basic parameter file containing a bunch of navigation parameters needed to operate the demonstration. Then we have the worlds directory. This contains our industrial simulation world. So this is actually the warehouse world we're going to be utilizing in this demonstration. And then finally, we have the scripts directory. And this is containing the scripts that we're using in our demonstrations. And you're going to see that there's basically three styles of things in here. So there's the robot navigator.py, and that contains the major working API code we're going to be utilizing in this demonstration. So that's what's actually calling the navigation stack to do certain operations. Then you're going to see there's also these kind of demonstrations like picking, security, and inspection. And those are some kind of like application demonstrations utilizing the API. And the third kind of class we have here is this Waypoint follower, Nav2 pose, and Nav3 poses, demos. And those are more or less just API demonstrations to show how you can utilize those APIs with the Navigation 2. But we're not actually going to be utilizing those today. But they're really nice to look through later if you're interested. So we can go back out to our ROS2 workspace in the second terminal. Let's see what we're doing here in the first one. Awesome. So we build all of our packages, so we know that things are set up the way that we want them to be. So the next thing we want to do here is then source that install file. So we're going to source that, and now we have access to. Oops, sorry. So now we have access to all that great stuff we just built. Awesome. So the last thing we're going to do here is also copy paste this command. This is basically just exporting all the different Gazebo model paths we require for this demonstration. So you're going to see that we have this Neo Simulation 2, which is all the robot models that we're interested in working with, as well as this AWS RoboMaker Worlds model file, which is going to give us access to the shelves and the boxes and whatnot that is being utilized in Gazebo for that world. So now that we've built this and we've sourced our Gazebo model path, we're ready to actually launch our first level simulation here just to see what we have to work with. So if we copy paste this ROS2 launch, Nav2 ROSDevDay 2021, system launch.py file. And it's going to take a moment here. And we'll see we have this Arvis window pop up here. So let's go ahead and full screen this. And we'll just zoom out here so we can see our full map in all of its glory. And you can see we have this Gazebo world now set up here. And you can see that we have this great warehouse world with our robot and the laser scan in it. And I'll just like scroll it here so you can see this robot. It's a pretty cool robot to work with in this great Gazebo world. And something else you're gonna notice here is that you're gonna see on the terminal all this garbage coming at you. And there's one of the big things that we changed about in ROS2 from ROS1 is that we don't actually default the position of the robot to the origin. So typically, if you start up navigation, it would just poof, put your robot at the origin of the map, and then later you'd say like set 2D pose estimate, and it would go to where you want to go. So we don't actually initialize at the origin because then you actually populate the cost map near the origin with all the information that's actually representing the area away from your map. So rather than clearing the cost maps on bring up or trying to like later clear that when you're actually in the navigation operation, we wait for you as a user to actually tell us where you think the robot is. And so you can do that through RViz with this 2D pose estimate tool that you probably are used to in ROS1. And let's just pick a random location here. So there you go. You can see all that garbage has stopped. And you can see that our lifecycle manager of Nav2 is activating all of our servers, and all the things are now online. And you can see that our robot is brought up in this location. You can see that's actually not really where the robot actually is in reality, right? Our robot is here off in this little aisleway, which we're referring to as the staging point for the robot for all these demonstrations. So if you were actually using this in a real application, rather than use that 2D pose estimate tool, you'd probably actually use something closer to this ROS2 topic pub. So you probably have some sort of application that remembered where your robot was last positioned or where your dock location is. And so in the second terminal, we're going to go ahead and just say, okay, let's publish this position as if we're in an autonomous system. And we're published this a few times, and you can see that robot, poof, it popped over here to this area that's pretty close to where we're starting. It's not quite right, but it's pretty close. And yeah, this is basically the basic demonstration for how to get Nav2 to run. And so, spend some time and play with it. Like have your robot use this 2D navigable tool to make your robot like drive somewhere. So we're gonna have it drive, to this arbitrary location. And you can see that our robot is responding to that and is be driving around. And what's nice about ROS2 is that this Nav2 goal post tool is now actually hooked up to the action server of ROS2 and not actually just publishing a topic. So you can see in our actual nice like RViz plugin here, we have some information that's being published to us, and also the ability to cancel navigation requests. So I hit the cancel button there, and you can see our robot has stopped because we just canceled the request. You can see that now we have this canceled state. So we're going to scroll down here. So you're going to see an example here of our RViz plugin with some active state. So let's do this again. So let's make our robot move to some other location over here. So you can see that it gives you this estimated time of arrival based on the robot's current speed and the length of path around you, the distance remaining, which is integrating the length of path along it. We have this time taken, and then also the number of recovery behaviors executed during this behavior. And then so we can cancel this again. And we can actually showcase some of the other great tools we have available to Nav2 as well. So if you see this Waypoint Nav3 poses mode, if we click this, then it's going to enter us into this accumulation mode. And so now if we use this Nav2 goal pose tool, we can actually create a bunch of different poses, and the robot is going to wait for us to finish selecting some places of interest for us. So now that we've selected 3 of these areas that we're interested in, you can say that you have a couple of options here. We can cancel this, which will bring you back into the main menu. We can start navigating through poses, and we're going to start waypoint following. So this navigate through poses, we hit this. You can see that our robot is frozen. That's fun. All right, let's try it again. So what you're going to see happen here is that our robot is going to create a path plan through these 2 poses and then go through all those poses at the same time. Why are we not happy? We're not happy at the moment. So we're going to go ahead and just Control-C all this stuff and try again. Sorry about that. So just as before, we're going to then set our initial pose through the second terminal, just to get the robot to be in the location we want to start off in. There we go. Cool. So let's go to that nav through poses button. We hit that again, and let's set a couple positions. Let's say here and here, and then we're going to start navigating through poses. There we go. And we're seeing now is that it's actually path planning through both of these positions. And it's not going to stop at this intermediate position. It's going to go right through it. So that's why it's called navigate through poses and not for instance, like stopping a waypoint. So you'll see here that the robot is just going to continue driving through this waypoint. And once it gets close, it's going to skip for that waypoint and head to that next one. Just before, we can go ahead and just cancel that, and it cancels that action. Then if we do another demonstration here of like doing another couple waypoints, and let's do the waypoint follower mode this time. So the waypoint follow mode, rather than navigating through those poses, is we go to each individual position and stop, execute some sort of behavior, and then go to the next position. And just the same way, we could cancel it, but actually we're done with this demonstration, so we can just go ahead and just Control-C out of this entire thing. Yeah, so that's the basics of interacting with Navigator 2 through RViz. You can see some additional videos here as well, and that's pretty much what we have to say about that. So moving on to section 2. So this section is really nice because we're actually going to be working with our actual like autonomy demonstrations we want to be utilizing with the direct actions that ROS2 provides you. So there are 3 primary actions that you have available to you: this navigate to pose, this navigate through poses, and this follow waypoints action. And so we're going to talk about these each one at a time and show a nice demonstration of a notional task that a robot is going to fulfill using these APIs. So the first one we're talking about here is this navigate to pose, and the demonstration we'll be walking through is like a picking autonomy challenge. So if you're someone like, let's say like Locus Robotics or Fetch Robotics or something, where your robot goes to a shelf and you have some person pick an item off a shelf, put on the robot, and tell the robot, cool, you have this item, move on to your next location. That's pretty much what we're doing here. So we're having the robot go to locations to pick an item and then go to some sort of shipping location for its final destination. So the navigate to poses action is pretty suitable for this point-to-point navigation type, which is what you expect when you work with navigation in ROS1. But it can also be leveraged for other point-to-point-esque type of tasks. And so actually one thing we have set up in navigation 2 is this dynamic object following task. So rather than just going from point A to point B with these both fixed positions, we can instead say, okay, I'm starting at my robot position, but I actually want to follow a dynamic obstacle. And that dynamic obstacle is actually starting at that position over there. And so what your robot will do then is then have start at your initial position, plan towards that dynamic obstacle. But then over time, the behavior tree for the dynamic obstacle following object following demonstration is then going to be picking that position up using some sort of perception task that you provide, and then it's going to be continuously updating that goal position. So your robot is then following behind your dynamic obstacle. So this action definition is pretty simple. We have the pose. This is the goal pose you'd like your robot to go to eventually. So whether this is your final goal position or the starting position of your dynamic obstacle that you'd like to be tracking. And then the second field here is this behavior tree. What's really nice about Nav2 is that we provide a default baseline behavior tree, which is really nice and will do most of what you need to have done for basic autonomy tasks. But if you want to have your robot have different types of behaviors, you can actually specify the behavior tree you'd like your navigation request to use on a per task basis. That means that you could have one robot that could have dozens of different types of behaviors. That you could have it following to this position, you could have it follow somebody through an area and then branch off and go back to a different task. And you can specify each of those things on a per navigation basis, but there's then a baseline behavior tree that'll be used if you don't specify one. Then we have this result object, which contains to absolutely nothing of value. And then we have this feedback definition. And this is new to ROS2, and so we provided you a bunch of interesting information that would be really useful to you if you're trying to build autonomy tasks on top of Nav2. So you're getting the current robot position so that your autonomy task can potentially just utilize this high frequency feedback rather than having a TF buffer itself. You also have the navigation time, which is the amount of time the current navigation task has taken. And this might be helpful for you if you say that my task should have taken 60 seconds, but we've now been navigating for over 10 minutes. Maybe then you should cancel this navigation request because clearly something's going wrong. We also have this estimated time of arrival, which is really nice for, estimated time remaining, which is also the same thing as estimated time of arrival. And that's also then tell you how much time you've left in your navigation task based on your current position, the length of the robot path, and the speed your robot is moving at. Then we have this number of recoveries parameter, or feedback, which is then very helpful for feedback systems to understand if your robot is doing what's supposed to be doing. If you have lots and lots of recovery behaviors executing, your robot might be in a bad position, and you might want to have an operator take a look at it to maybe get it out of that bad position. And then the final one is this distance remaining, which, like I said prior, is basically integrating the path length over time, so that you can know how much distance left there is to your goal. And this paragraph down here basically just explains what I just mentioned. So the picking demonstration we're going to be utilizing is going to use this navigate to pose task in order to go to particular locations. So this is basically what you expect to work with in the navigation task. And so looking over this picking demonstration.py, which is in that scripts directory in the package we looked at prior to it, you're going to see this some of these key lines. So these are abbreviated demonstrations of basically the core of the algorithms, but you can actually go into the scripts yourself and take a look at all of what's happening there. But this is kind of the core of it. So we're creating an instance of our basic navigator object, which is given to us from that robot navigation.py script. And so the first thing we're doing is setting our initial pose. And since our robot is starting at this staging position that we can imagine having a bunch of robots lined up at, waiting for tasks for them to execute. And so we're starting a robot there. And so we tell the navigation task that, hey, we're starting at this position that you can utilize. And then we're going to wait for the navigation system to actually fully bring up. So we don't want to be telling our robot to go to position while it's still bringing up in the lifecycle management system, or there's some error going on, so that task would be immediately rejected because there's problems. So that's going to block until our navigation stack is nice and ready for you to actually set a command for it to follow. Next, we're going to be using this go to pose API command, which is going to basically just, behind the scenes have this navigate to pose action client it's calling. And we're going to give it the position of the shelf we're interested in going to. So in this demonstration, if you read the code, what I say is we have this sample request come in from a user to say, I want to be going to shelf C, which has some product that they're interested in picking, where a person will come and pick that product and put it on the robot. And then we're going to be going to a pallet jack for the robot to drop off the item for the shipping receiving department. And so this go to pose command, just like all the commands you're going to find later in these demonstrations, is actually non-blocking. So what an IBM implementation might do is say go to pose, and it'll just block your thread until it's complete, and just say, hey, cool, I was completed, or I failed, or I was preempted, or something. But doing so doesn't actually allow you then to have single thread applications doing other stuff at the same time. And the ROS2 implementations of action servers actually give you a lot more flexibility there. You've always been able to do it, but the simple action server, I think, blocked primarily in ROS1, but admittedly, it's been a little while since I've used it, so don't quote me on that if I'm wrong. So instead of blocking, we're actually going to enter this while loop where our navigator is going to request saying, hey, is our navigation task complete? And if it is complete, then we can get our result from the navigation system through the get result API function. And then go to our next destination because we want to go to that shipping destination that's in our request. One nice thing about this while loop is actually then we can actually utilize our feedback. So we can use this get feedback API to actually print some information about our task, or maybe we want to check on the robot status to see if there's something that's gone wrong. But we can do basically anything we want to do in that while loop in case there's some useful information you want to be using in the single thread application. So because we still have these two terminals open and we've already sourced the the up-ROS Galactic, and we've already set up our Gazebo model path, we can continue using this first terminal pretty much for the rest of this demonstration. So if we copy paste this same line that we were running before, you're gonna get this nice ROS2 launch Nav2 ROSDevDay 2021 system launch.py. And in our second terminal, we're going to be launching our autonomy script. And since I actually don't remember if I sourced this in our first one, so let's go ahead and source that again in the second terminal. And this is our autonomy script we want to be running here. So we're actually gonna hit enter on this autonomy script first. And something I want you to note here is actually you see how it's saying publishing initial pose and it's still waiting for things to come up. And so this is the nice thing about blocking until Nav2 is active. That's exactly what's happening here in this wait, is that Nav2 isn't active yet, so it's not going to be doing anything yet because the navigation stack isn't ready for a command to be sent to it. And so it's going to block it like this indefinitely until the navigation stack is actually ready to process your command. And so we're going to go ahead and hit enter here. And very cool. We now have our simulation set up. Scroll over here. And you can see that now our robot is doing exactly what we asked it to do. It's going to be going to this initial position at shelf C. I'll scroll here a little bit. And our robot is then following in between these areas that are blocked up with safety tape. We're going to look at later at the keep out maps, but there are actually keep out maps right now enabled so that the robot doesn't want to drive through these areas if it has any other option. And let's go back to our autonomy script. And you can see that actually it's been printing saying, hey, estimated time of arrival at shelf C, where we asked it to go to, was counting down basically from the time it estimated. And now that it's actually got that product to shelf C, we're going to be bringing that down to that shipping destination. And the robot will then go to that shipping destination. And you can see here in this video, it's a sped up version of this exact same process here in the IPython notebook. And so you can see again that our robot is driving between these safety zones to go around them in order to get to that pallet jack, which you can see our simulation is over here for the shipping and receiving department. Just for brevity, so we can continue moving on to the conference and we can stay on schedule, we're going to go ahead and just Control C out of this demonstration because I think we've gotten the point. It's going to stop there to deliver that item to the shipping and receiving department. Awesome. So we can start now with our second demonstration here, which is this navigate through poses API. And so if you actually look at our scripts, you're going to see that what we're using is a security autonomy task. And so if you have a security autonomy task, you don't want your robot to just go to this position, stop, and then go to that position, stop, and go to this position, stop, right? That's kind of useless, right? You probably have some sort of like people behind the scenes that are like looking at this video feed data to see if there's like someone robbing a car, or maybe you have some artificial intelligence systems behind the scenes checking for anomalies. But either way, there's really no reason for your robot to actually stop at each of these positions. And so this navigate through pose API is really nice for that, because then you can set up this predefined route that's interesting to you about areas that you want the robot to travel through to collect data or video feeds. But you don't want your robot to actually stop in those given positions. And if you make this sparse enough, then if there's actually obstacles in the way, then the robot will just dynamically move around those obstacles while it's performing its task. And so this navigate through poses action is pretty well suited for any sort of pose constraint navigation requests. So like I said, if you want to go through these positions over time, but you don't want to stop at those positions, this is really useful. With the NavFN planner that we're using in these demonstrations, it's a non-kinematically feasible planner. It's basically a naive grid search, so it's not respecting any sort of kinematic constraints of the robot. So what you'll see is that at each of these positions, there's a hard cusp at the waypoint. If you actually use a path planner like the Nav2 SMAC planner that is actually kinematically feasible hybrid A*-based planner, then what you'll actually see through this is that you'll get smooth, continuous paths through all these waypoints as being not just hard position constraints, but hard pose constraints. So it will reach each of those positions at a given orientation vector, as well as the plans actually being very smooth throughout the entire trajectory. So that could be nice if you want your robot to have very smooth motion throughout your usage, even if you're not using a non-circular robot or you're not using a legged or an Ackerman steering robot. So the definition here looks very similar. Rather than having a single pose you want your robot to go through, it's going to go through a series of poses where that last pose, it will stop at that final pose. We have a behavior tree as well to specify a specific behavior tree. Our result is also empty. And we have the exact same feedback here. The one thing to note here is that now we have this additional field, this number of poses remaining. And the number of poses remaining field is basically me telling you how many of these via points do you have remaining left in your trajectory, which is a nice debug instrument for analyzing feedback to see if you're progressing along your route. So here's our basic demonstration. I talked a little bit here about what we're interested in doing here. And here's the code we're going to be working with. So like before, we're going to create instances of this navigator. We're going to be setting our initial pose to that staging position the robot is starting at. And we're going to wait until the navigation system is up and ready. And then rather than just going to one position, we're actually going to put this entire thing into a while loop, where we're going to be going through all the positions of our security route that we have predefined. And then while we're waiting for the navigation system to be complete, we'll be printing information about the number of waypoints remaining. This is also a great place you might want to have your machine learning algorithm, like capturing images and processing them and doing that on a continuous basis while your navigation system is continuing. So actually, you could do this entire security task in a single application and also in a single thread, which is pretty cool. And then actually, we're going to be then reversing this security route. So we're going to go from start to end, and then end to start, and start to end, and end to start. And we'll be continuously bouncing back and forth. And that's really nice to say, like, rather than just going to this route once and then docking, you want your robot to continuously moving. Robots are expensive. They're being paid to do security. So, hey, this thing should be continuously moving around the route and not just like stopping after one instance. So that's actually what this while loop is here to do. So we can do the exact same thing as we did before. In our first terminal here, we're going to do this ROS2 launch Nav2 Dev Day 2021 simulation.launch.py. And we can go ahead and hit enter and let that come up. And in our second terminal here, we're going to be using the security task instead. So we're going to be copy pasting this command. I'm going to go ahead and just full screen this and then adjust these windows before I run this because I think it's a much more useful demonstration if you can actually see from top down. And over here, we'll scroll out so you can see more. So there we go. You can see where our robot has initialized in this position and it's starting this route. So you can see our robot is I know it's hard to see here, but there's a waypoint here, there's a waypoint here, there's a waypoint here, waypoint here, one somewhere around here, and then one at the very end here. So because a straight line path will be going right through that forklift, because we've made this, generally speaking, a very sparse path, because we just want this general route for the robot to follow. But for any given local area, we want the robot to be able to have the flexibility to move around dynamically also as well. So you can see here that our perception system is picking up this forklift, and you can see that the LiDAR scattering here. And so the robot actually going around that forklift and then coming through back around to our security path, which is also then following this green safety tape area. For a sped up version of this, because I know that the simulation is running fairly slow, you can see, I think, a 3x sped up version of this here. So the robot that goes to the end, and it's going to bounce right back and go back and forth and back and forth and back and forth over time. And so this will be an endless security task that's going to be utilizing. And I think what you're seeing here is a little oddities involved with the fact that I have the keyboard zones enabled, where in this demonstration I did not. So I apologize for that. I did not properly reset my simulation environment before the demonstration, it appears. So I apologize for that. But you can take a look here at this nice video, and you can actually see what should be happening here. So we're going to be going through and around, through and around. And so what you saw on my simulation here was that the keyboard zones were basically making havoc trying to go around the forklift in this situation because I didn't disable the hard constraints against going around. So moving on to our waypoint follower demonstration. So in this demonstration, we're going to be using a demonstrated inspection autonomy task. And so a common thing that folks have to do in warehouses or retail stores or really anywhere that there's shelves with lots of stuff is you have to know where the stuff is and how much stuff is there. So companies like Fetch Robotics has a tower for RFID tags. My previous company, Simply Robotics, does this with front of house retail shops. And basically the task is to go around, take a bunch of pictures, and understand what's on the shelf using your machine learning algorithms. So we're going to be using the waypoint follower. We're going to be creating a proof of concept of an inspection task. So the follow waypoints action has this set of poses. And so these are each of the poses you'd like your robot to go to. And the result here is actually meaningful. So now we have this number of missed waypoints, which is a vector of the waypoint IDs that the robot was unable to achieve. There's a parameter in the waypoint follower server that says, if I fail waypoint, should I continue on to the next waypoint or should I exit the task? And so if you set it up so that it doesn't exit the task and continues on to the next waypoint, then at the very end, it will tell you which of the waypoints it is that you missed, so you can cache that information for later utilization. And then the feedback is very simple. It's just giving you that current waypoint. And since the waypoint follower server is actually utilizing the navigate to pose server under the hood, you actually then can access the feedback attained by the navigate through pose server. So you still have access to all this great information about your current pose, estimated time of arrival of your current waypoint, all that kind of good stuff. So you actually have access to all the information for this case as well, but it's not provided directly through this API. So the nice thing about the Waypoint follow server as well, as we have these task executor plugins. And so rather than just going to one position, stopping, and then just going to the next position, we actually have a plugin lib-based plugin system for task executors at each waypoint. So the robot stops the waypoint, it'll say, do I have task executor plugin? If so, execute that plugin. And that plugin could do anything from capture an RFID scan, take some pictures, log its position and space, whatever it is that you're interested in doing. For a picking task, for instance, this might be waiting for user input, that a user has pressed a button saying that, hey, I've put the product I'm supposed to put on this robot on the robot. And so you can set up any sort of task executors you like. We provide image capture, waiting, and wait for user input plugins by default. And we're always willing to expand those if there's more of that folks think are generally useful. So for the waypoint following demonstration, if you look over this inspection demonstration.py file, you're going to see basically this core set of algorithms, which is creating this navigator in the initial pose and waiting for it to come up again. And the big API here is this follow waypoints object. And so that's what's actually method. And that's actually what's going to be calling the waypoint follower server for you under the hood. And we're giving this a vector, or in Python, a list of inspection points, which are basically a list of post-stamped positions. And while we're waiting for it to complete, we're going to do some stuff. And so in this demonstration, we're going to be publishing feedback about the number of waypoints that's currently has gone through so far in its current task. And once it's succeeded, we're going to be going back to this initial pose so that it goes back to the staging position for another request to go inspect some other area. So we're going to be going back to that initial position so that it resets. This can be utilized over and over again.
Steve, 5 minutes.
Okay. And there we go. We can see, we can go ahead and just launch this. And we'll be using this inspections.py file here as well. Let's go ahead and maximize this. And let's go ahead and run it. So what you're going to see is that the robot is going to be inspecting these shelves, the shelving units at the top of the screen here. So it's going to be going to the center of each of these shelves and taking a picture, and going to the next waypoint, taking a picture of the shelf, and continuing on. So in this video you see here, this is a sped up version of it. But essentially we're going to be going to each of these waypoints that are between these two shelves, and then going to the position to take the image that we're interested in taking and going to the next position. And so what you'll see actually different in the demonstration that I'm providing you here versus the one you're seeing in the video is that because I actually already have the cost map filters, keep out zones enabled, you're actually seeing that we already have a cost map keep out zone set up for these shelves. So rather than the robot going underneath these shelves like you see in the video, the robot is actually going around those shelves out into the aisle, into the next shelving area. So we're not going underneath these shelves for safety. So we don't have time to go through this, unfortunately, but fortunately for you, we actually had these keep out zones enabled through the entire demonstration. So that's why you're seeing what you're seeing here in this demo, which we can keep having play. And so in ROS2, we had these keep out filters, which are speed restricted zones as well as keep out zones. And so you can see in this keep out zone mask, we've masked off these safety taped areas as well as the shelves area in our example warehouse. And so that's why when we were doing our picking task, the robot was going around the safety tape into these little aisleways. And now in this inspection demonstration, that the robot is going between the shelves and not under the shelves, just due to these keep out zones that we've set up. And while we're not going to use it in this demonstration, you can also invert that logic so you can have preferred lanes of travel. So your robot will prefer to go to these lanes, but can leave the lanes when necessary, but will, generally speaking, stay within these safety lanes if there's particular areas the robot needs to stay within for safety regulations. But it has the flexibility that the robot can leave those areas if there's something blocking it, like a forklift or something. So the configuration you're going to see here, unfortunately, we don't have time to go through this in our YAML file, as well as in our launch files, are these parameters. So basically, we're just adding this cost map filter and setting the parameterization so we can launch both the cost map filter plugins, the parameter server, or sorry, the map server required to expose that keep out map, and our cost map filter info server, which is exposing information about our cost map filters. And you'll see basically the analogs for this in our launch files. And you actually, rather than having to put together for a demonstration at the very end here, actually the demonstrations we've been utilizing this entire time has actually been utilizing these keep out filters by accident. But let's say it's on purpose because we're running low on time here. And so I managed to sneak in all the information during our talk. And yeah, that's about it. So, Nav2 is a really powerful tool, and it continues to get more powerful. You can see how you can follow waypoints and execute particular tasks. You can go through many waypoints, have pose constraints to influence the direction your robot travels, or you can just have your robot be fully autonomous and go to do point-to-point navigation. We also enable keep out filters to make sure that the robot stays out of areas or doesn't want to go into areas it shouldn't go into if it has other options, as well as set up speed restriction zones so the robot slows down or speeds up in certain areas that you might find are unsafe or are problematic. If you want to get involved in ROS2, Nav2 rather, you can join our working group meetings or contact the team. If you want to get started with it, you can see navigation.ros.org. I've spent a great deal of time writing documentation there, so there's a lot of great stuff there. And if there's anything missing, feel free to let me know, and I'll make sure to add it. We're always open to contributions from anyone with any skill level. So if you're a student or a professional software engineer or a researcher, there are projects that are suitable for all of your interests. If you get in touch, I'm sure we can find some sort of project that would be suitable for you to work on. Or if you have a project already in mind that you'd love to work on, please share it with us, and I'm sure that we'd be interested in trying to get that information or that capability in Nav2 as well. And with that, I can take some questions here. But you can see that our robot's now going back to our staging position so that you can request a new inspection task if you like.
Thank you very much, Steve.
Thank you.
Thank you. Can you please stop sharing your screen so we can see you, and then we can go to the questions. And for the audience, then if you have any question, you can go to the tab that is on the panel of the conference. It's called Questions. And then go there and put your questions there. And also you can vote the questions that somebody else has put there because you consider they're interesting. Then we have already, Steve, we have already a lot of questions there. So your presentation has been creating a lot of interest, and people have very nice questions. Let me start one. I think it's more simple to start while the people is putting more questions and voting. And the first one is from Pablo Puente, and he says, what are the main improvements in Navigation 2 in Galactic versus Foxy? And I would rephrase so some features that are only available in Galactic but not in Foxy for Navigation 2.
So it's funny you bring that up. One of the things we offer in the navigation.ros.org website is these migration guides, and these contain all of our big changes that I felt were interesting for people to be aware of between distributions. So if you want the exhaustive list, if you go to navigation.ros.org/migration/foxy.html, you'll be able to find that information. But I pulled this page myself to actually take a look. The big updates are we've added all the feedback that you saw that we had during the demonstration, like the time remaining and the number of recoveries. All of that was added between Foxy and Galactic. The actual navigate through poses capability of going through many positions, that was added between Foxy and Galactic. We've added new controllers like the regulated peer pursuit controller and the hybrid A-star path planner. We've added goal checker plugins as well as the task executor plugins. We have group support. We have the cost map filters were added. We have a new theta star planner.
Wow.
I mean, I might have halfway through this list. So there's a bunch of stuff we've added between that. This is extremely active. We are interested in adding new features. We're serious about making this the best navigation system in the world.
Impressive. And any chance that those features are going to be ported to Foxy, or we are moving forward as the distributions of ROS2s are moving?
We're moving forward.
Okay.
So I backport what we can. The problem is that many of these things, especially like feedback, are like very implicitly API breaking changes, right? You just change the definition of the message that people are utilizing in production today, and we can't do that. We can't be messing with stuff that people are trying to build products around. So we're very serious about API and API compatibility. So we backport what we can. But you must understand. Yeah, we're focused on the future at pretty much all times.
Makes perfect sense. Yes, and let me here ask you the most voted question. Many people has voted this one. Is by Marcos Barrera, and he says, "Hello, Steve. Are there any existing full coverage of path planners in ROS2 Navigation 2 currently?"
Full coverage path planners, I assume is, sorry, what that meant. Not that I'm aware of, but it's not something that there's no reason why it couldn't be done. I think that's a pretty use case specific kind of task, right? So there are optimal time or optimal distance type configurations, depending if you want like a lawnmower configuration or a Roomba configuration. Those are very different kind of requests. So we haven't added one in Nav2 directly because of the very difference in kind of the fundamental breakdown of what you need for a full coverage planner. But if someone's interested in contributing one or both of those, we'd be certainly interested in talking about it. We've previously had conversations with GreenZ that has a full coverage planner, as well as Nublio that also has their own full coverage planner. But those are both available in ROS1, and it would be pretty trivial to port to ROS2. But so far, not directly available through Nav2 and ROS2.
Okay, I think that adds a very good opportunity for the audience there to participate and to contribute to the navigation to port other planners that they may be interested in. And then let me see here another question, which is, okay, so does the navigation to focus on multiple robot simulations? It means about doing navigation of several robots, and if yes, how collision avoidance and prioritization is done?
So actually, if you go to our Nav2 bring-up package in the bring-up directory into our launch files, there's right now already an example for you for a multi-Turtlebot 3 simulation.launch file, which is bringing up, I believe, 2 robots in the Gazebo sandbox world. So that's all been working. That's been a big feature from even the very beginning that even ROS1 had. So that's all ready for you, and there's no reason to expect issues.
Okay, great, awesome. And it says here, let me see, another question. Okay, so I don't understand this one very much. By Nitin Diman, that he says, is it possible to pass a specific path to the robot to follow in a particular shape? I'm asking you because it's very well voted, but I think that this is already done by the path planner. But what would you say about that?
I think what they're asking is if I have a pre-computed path that I'd like to follow through space that isn't being computed live by a path planner. And yes, you can totally do that. So that's some of the great parts of having these modular servers that usually just run independently, as well as having this behavior tree logic that rather than calling the compute path to pose to access a path planner to create dynamically your plan from point A to point B, instead, you could just cache it from a file and then send it over to the follow path tasks directly in the behavior tree. So you can completely bypass the path planner with exactly one change to the XML file for the behavior tree.
Okay, thank you. Let me check for a final question here. It's George Cosmin that it's a very long question, but let me just simplify a little bit. And he's interested about adding the keep up zones by means of code. I mean, programmatically add those if this is possible to be done, or you have to do it previously by pre-processing the map. Is it possible
I
to?
don't understand the.
Okay, yeah.
I
So
don't understand the intent.
okay, so he says about he would like to create programmatically the keep out zones in the navigation, so areas where the robot doesn't have to be moving inside. But as far as he knows, those areas, they have to be pre-done before you launch the navigation system. So is it possible to do it while the navigation 2 system is running and then decide on the spot and do it by a program and decide, oh, from this point to this other point, you cannot traverse, you cannot move around there?
Yeah. I understand. Yes, you could do that. And actually, there's nothing you need to change about it either. That's default behavior. So we have the keep out filter is a cost map layer, and we want to keep the design of it as similar to other things in navigation as possible. So what you'd expect to find in the static layer is that you're receiving a map topic, and then you're creating the static map from that map topic. And every time you get map updates from that topic, then that's being reflected back in your cost map. And so that's exactly the same thing that's happening in the keep out layer. We're subscribing to a map topic, and if you update your map, that map topic, it'll dynamically adjust to that new topic you've just requested.
Okay, makes perfect sense. Yes, okay. So I think that we are finished with the questions. Thank you very much for this awesome presentation, and especially all the code that you are providing there that is working and showing the navigation to package running. Thank you so much. So valuable. Thank you very much.
Awesome. Cheers.